In the last video, we talked about the factors that affect the stability of negative charges. It turns out that we can rank these factors in importance. The most important is usually atoms, followed by resonance, then induction, and finally orbitals. This ranking is not absolute, and we'll find exceptions. In fact, we'll be talking about exceptions, but it works for general purposes. Okay, so let's determine which of these two protons is more acidic, the blue one or the red one. First, you'll note that the red one has a negative charge on an oxygen atom, and that's more electronegative than the charge that's on the carbon atom of the blue figure. But then let's check our resonance, because these electrons here can make a double bond here and push these electrons onto that carbon atom. So we'll get a secondary figure that will look something like this. It'll have two extra electrons there and a negative charge. These electrons can then travel to here and place the negative charge on the end. Then these can also travel to here. These electrons involved in this pi bond will then reside on that carbon atom. And so this negative charge, it turns out, is spread over one oxygen and 3 carbons. So let's see if we take the blue proton off, what we get. We're on a carbon. These electrons can make a double bond here and push the pi electrons here to reside onto that end carbon. We get this. We'll get a double bond here, double bond there, and we'll have a negative charge on the terminal carbon. These extra electrons can make a pi bond here, pushing these pi electrons onto that carbon. So what we'll end up with, oops, get rid of that pi bond. It's a negative charge here. The negative charge is on 3 carbons. So the red one is going to be the more acidic one. It's going to be the one that has the charge spread over more atoms and more electronegative atoms. We look at the next one. Well, in this case, both of them are on carbon atoms. In both cases, if we take the red proton off, the charge will be on this carbon atom. If we take the blue one off, the charge ends up on that carbon atom. But let's see what resonance figures we can draw. For the red one, if we take off that middle proton, we can get a double bond here, and it can go up there. So we'll get the charge on an oxygen, which would be advantageous. We can also go the other direction. These electrons that are in the middle can go this way and make that figure. We'll use that color to do that figure. Okay, so for taking the proton off the middle here, we get it spread on a carbon and 2 oxygens. If we take the proton off the end, these electrons can go here and go up here. We only get one figure. It can only go to that one, to the one oxygen. And so, as you would expect, we've got one carbon and one oxygen. So that makes this one much more acidic because it spreads its charge over a carbon and two oxygens. Okay, so our last one. If we take, to get it all on here, if we take the red proton off, we get this figure. The charge is spread over this oxygen. It can also, through resonance, be spread to this oxygen. So we have two oxygens. If we take the blue proton off, it's spread over two nitrogens. And so that makes this one more stable because oxygen is more electronegative. There is one exception that I want to talk about, and it's because we actually use this reaction. If we compare acetylene, and this is supposed to be a triple bond is what I'm trying to express here with the equal signs and the underline, acetylene and ammonia, we make the conjugate basis. We end up with this, with a negative charge on a carbon and a negative charge on the nitrogen. Your rule says that the nitrogen is more electronegative, and so it would be more stable, and so ammonia should be a stronger acid. Okay? Follow that logic? However, in this case, the acetylene is the stronger acid. So this is an exception. In this case, the closest of that orbital, that sp orbital, compared to the sp3 orbital, trumps the type of atom. So we will see exceptions to our little rule I gave you, but it works for many things.